So right here in purple, in the dark purple, we have a non-specific immune cell. So this could be anything, any of the granulocytes or antigen-presenting cells. It recognizes the presence of a pathogen, in this case another bacteria, and it will start secreting both its granules, which are designed to destroy the pathogen from the outside in. It's similar to complement, except that these are secreted by granulocytes, and they're less enzymatic than the complement system. So what I mean by that is, if you have a granule producing cell, so here we have granule, and then we have all these things inside. So remember, these do include some enzymes, but there's also a lot of chemicals that are damaging. A couple examples are nitric oxide, which is toxic to bacteria, but you're also going to have things like hydrogen peroxide, hypochlorite. Like hypochlorite is bleach, and you will have some enzymes like lysozyme, which I mentioned. Lysozyme. So that is what is going to be found in these granules. Remember, granule producing cells are these guys over here: mast cells, basophils, eosinophils, and neutrophils. So you have your granule, and then it recognizes pathogens, so it's going to start exocytosing this granule. What that looks like is just typical exocytosis. There are going to be proteins that help fuse the granule with the membrane, so that this step right here, and then it will just push everything out into the extracellular fluid around it, and then these will start attacking the pathogen, whether it's viral, bacterial, or fungal. But again, these are highly toxic also to our own cells, and so this will start causing cell damage at the site of infection. And it will also harm the immune cells that are secreting them. So a lot of times these innate immune cells are going to die in the process of fighting an infection. So there is some collateral damage. But as this is occurring, this last step is occurring, it's going to form basically a chemical gradient at the site of infection. And as you get further away from the infection, it becomes less and less concentrated. But our immune cells, all of them, are tailored to follow concentration gradients. So that's what this arrow is, from least concentrated to more concentrated area, to be able to find this infection site to undergo the same sort of reaction. So if this is going to be something like a macrophage, then it's going to start phagocytosing bacterial cells, chopping them up, presenting them to activate T cells, which will then activate additional macrophages and B cells. B cells can do the same thing. If this antibody is capable of recognizing any of the bacterial antigens, then B cells can go to T cells, which then activate B cells. So everything, remember, is a web of interaction. So these will present, and then these will activate them. So T cells, though, are definitely the most, you could say, sophisticated of the immune cells, because they're responsible for recognizing pathogens being presented on MHC molecules, as well as activating all of the other immune cells using cytokines. So now if I cover that up and I say that this center one is a T cell, I can say that T cell cytokine secretion can activate additional immune cells around it. So if these were, instead of bacteria, again, I'm just going to cross it out because we're done with that. So if these are like eosinophils or neutrophils, and this is a T cell secreting cytokines, the cytokines in this area are going to tell these other immune cells to basically increase their activity. So whether they're phagocytic cells, they will increase the amount of phagocytosis. If they are like basophils and mast cells, it can cause degranulation to occur. I didn't give this a name. This is degranulation, this process. So degranulation is just exocytosis of toxic granule-containing vacuoles into the environment. Degranulation. So T cells can increase degranulation by immune cells, which again will harm invading pathogens as well as our own cells.